The universe contains events so violent they outshine a billion galaxies, yet happen in complete silence and darkness. Black hole collisions release more power in a fraction of a second than all the stars in the observable universe combined, warping the fabric of space and time itself. And we only discovered how to detect them a decade ago. September 14, 2015 changed everything. At exactly 9:50 and 45 seconds Universal Time Coordinated, two facilities in the United States, separated by thousands of kilometers, recorded something extraordinary. A ripple in spacetime itself, traveling at the speed of light, reached Earth after a journey lasting 1.3 billion years. The signal lasted less than a second. But that brief chirp represented two black holes, each dozens of times more massive than our Sun, locked in their final death spiral before colliding at nearly half the speed of light. The energy release was staggering. In the last 20 milliseconds before merger, these black holes radiated power equivalent to 3.6 times 10 to the 49th watts. Think about that number. Every star in the observable universe, all 100 billion galaxies, each containing hundreds of billions of stars, all shining simultaneously. The collision outshone them all. And this happened not through light or heat or any form of radiation we can see, but through gravitational waves, ripples propagating through the structure of spacetime itself. Here's what makes this even more remarkable. The distance that ripple traveled to reach us, it changed the length of our detectors by 1,000th the width of a proton. Imagine stretching the distance to the nearest star outside our solar system by the width of a single human hair. That's the proportional change we measured. And from that impossibly tiny distortion, we reconstructed an event that occurred when Earth was still dominated by single-celled organisms. But September 2015 wasn't just about one detection. It opened a door. Before gravitational waves, we observed the universe through light. Telescopes captured photons emitted by stars, galaxies, and exotic objects across cosmic distances. Yet black holes, by definition, trap light. Their gravitational pull is so intense that nothing, not even electromagnetic radiation, can escape once it crosses the event horizon. When two black holes collide, there's no flash of light, no burst of X-rays, no glowing debris field. Just two invisible monsters, spiraling together in darkness, releasing energy that shakes the universe itself without illuminating anything at all. That's where gravitational waves changed everything. Einstein predicted them in 1915, a consequence of his general theory of relativity. Space and time aren't separate entities but woven together into a four-dimensional fabric called spacetime. Massive objects create curves in this fabric, like bowling balls on a trampoline. When objects with extreme mass accelerate, particularly in asymmetric ways, they send ripples through spacetime itself. Einstein's equations describe this perfectly. But he never believed we'd actually detect them. The signals would be too weak, the technology too far beyond reach. For a century, he was right. Scientists built increasingly sensitive instruments, searching for these cosmic whispers. The challenge was unprecedented. Environmental noise from traffic, ocean waves, even thermal vibrations in the detector materials themselves threatened to drown out any signal. The instruments needed to measure changes smaller than the nucleus of an atom across distances of several kilometers. It seemed impossible. Then came LIGO. The Laser Interferometer Gravitational Wave Observatory consists of two identical facilities, one in Hanford, Washington, the other in Livingston, Louisiana. Each facility has two arms, each 4 kilometers long, arranged in an L shape. Powerful lasers shoot down these arms, bounce off mirrors, and return. When a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. The laser beams travel slightly different distances, creating an interference pattern that reveals the wave's passage. The sensitivity required is almost absurd. We're talking about detecting a change of 1/10,000th the diameter of a proton. To put that in perspective, if you could measure the distance from Earth to the nearest star with that precision, you'd need to account for variations smaller than the width of a human hair. Every truck driving past, every distant earthquake, every microscopic thermal fluctuation in the mirrors had to be filtered out, distinguished from a real gravitational wave signal. And on that September morning in 2015, both detectors saw the same thing, 7 milliseconds apart. The time delay matched exactly what you'd expect for a wave traveling at light speed between the two facilities. The signal's shape, its frequency evolution, the way it chirped upward before cutting off abruptly, all of it matched theoretical predictions for a binary black hole merger with extraordinary precision. The source, designated GW150914, involved black holes of approximately 36 and 29 solar masses. Over billions of years, they'd been spiraling closer together, their orbit gradually decaying as they radiated gravitational waves. For most of that time, the changes were imperceptibly slow. But as they drew nearer, the pace accelerated. Millions of years became thousands. Thousands became decades. Decades became minutes. In the final moments, physics gets wild. The black holes were orbiting each other hundreds of times per second, whipping around at a significant fraction of light speed. The gravitational waves they emitted grew stronger, their frequency rising like a siren. Then, in less than 2/10 of a second, they merged. Two separate event horizons became one. The collision produced a single black hole of 62 solar masses. Wait, that math doesn't add up, does it? 36 plus 29 equals 65, not 62. Where did those three solar masses go? Energy. Pure energy, radiated as gravitational waves. Einstein's equation, E equals mc squared, works both ways. Mass converts to energy during nuclear reactions in stars. And during black hole mergers, mass converts to gravitational radiation. Three entire solar masses, converted completely to energy, rippling outward through spacetime at the speed of light. That's the equivalent of annihilating 3 suns worth of matter in less than a second. To understand how extreme that is, consider our sun. It's been shining for 4.6 billion years, converting mass to energy through nuclear fusion. Over its entire lifetime, it will convert less than 1% of its mass into energy. These black holes converted 3 entire solar masses in a fraction of a second. The peak power output, in those final milliseconds, exceeded the luminosity of every star in the visible universe combined. And this happens in complete silence. No sound waves can propagate through the vacuum of space. The merger occurred 1.3 billion light-years away, in a region of space utterly devoid of gas or dust. No witness, no observer, nothing to see or hear. Just space-time itself, convulsing from the violence of the collision. Since that first detection, the catalog has grown exponentially. As of early 2026, LIGO and its international partners have detected 391 gravitational wave events. Most come from black hole mergers, though neutron-star collisions and hybrid events have also been observed. The fourth observing run alone, spanning roughly 2 years, produced over 200 candidate detections. Each one represents a cosmic catastrophe, played out billions of years ago, the ripples finally reaching Earth to tell their story. The detections reveal patterns we never anticipated. Take GW241011, detected in October 2024. The collision involved black holes of 20 and 6 solar masses, occurring about 700 million light-years away. On the surface, nothing unusual. But when scientists analyzed the spin of the larger black hole, they found something extraordinary. It was rotating at 69 to 87% of the maximum theoretical spin rate for a black hole. That's bizarre. When massive stars collapse to form black holes, they typically don't spin that fast. The rotation rates are modest, well below the theoretical maximum. But if a black hole forms from an earlier merger, it inherits the spin of its parent black holes plus additional angular momentum from their orbital motion. The result is a black hole spinning far faster than stellar collapse alone could produce. GW241011 wasn't a simple merger. It was a second-generation event. One of the black holes had itself formed from an earlier collision. The evidence is written in its spin, in the way it rotated as it spiraled toward its companion. We're seeing hierarchical mergers, black holes that formed from previous mergers, colliding again in a cosmic chain reaction. This changes how we think about black hole populations. In isolated binary systems, two stars orbit each other, evolve, and eventually collapse into black holes that merge. But in dense stellar environments, like globular clusters with hundreds of thousands of stars packed into a relatively small volume, black holes can encounter each other dynamically. They merge, producing a larger black hole that remains in the cluster, available to merge again if it encounters another black hole. 1 month after GW241011, another hierarchical candidate arrived. GW241110 involved black holes of 17 and 8 solar masses, merging 2.4 billion light-years away. The larger black hole was spinning at 21 to 94% of the maximum rate. But here's the twist: its spin axis was anti-aligned with the orbital plane. It was spinning backward relative to the orbit. That configuration is extraordinarily difficult to produce through normal stellar evolution. When binary stars form from the same molecular cloud, their spins tend to align with their orbital motion. Everything rotates in roughly the same direction. An anti-aligned spin suggests a chaotic formation history, consistent with dynamical encounters in dense stellar environments where black holes can collide from any direction. These discoveries point toward a hidden population of second and possibly third-generation black holes, objects born from multiple merger events, growing progressively more massive with each collision. They challenge our models of black hole formation and force us to reconsider where and how these mergers occur. But the detections also revealed something completely unexpected, events that shouldn't exist according to our standard models of stellar evolution. In November 2023, LIGO detected something that fundamentally shouldn't exist according to everything we understand about stellar physics. The signal, designated GW231123, arrived from a collision billions of light-years away. When scientists analyzed the data, they found themselves staring at a cosmic impossibility. The merger produced a final black hole of approximately 225 solar masses, formed from the collision of two black holes weighing roughly 100 and 140 solar masses each. That doesn't sound dramatic until you understand the forbidden zone. Stars that collapse into black holes can't produce remnants between about 70 and 140 solar masses. It's not just unlikely. It's physically prevented by a process called pair instability supernova. When extremely massive stars reach the end of their lives, their cores become so hot that photons spontaneously convert into electron-positron pairs. This removes pressure support. The core collapses catastrophically, triggering a thermonuclear explosion so violent it completely destroys the star. Nothing remains. No neutron star, no black hole, just expanding gas dispersing into space. The mass range where this occurs is well understood. Stars massive enough to undergo pair instability don't leave behind black holes in that forbidden mass gap. Yet here was GW 231123, a collision between two black holes squarely within that gap, producing an even more massive remnant that also shouldn't exist. The most plausible explanation brings us back to hierarchical mergers. Both black holes likely formed from earlier collisions of smaller black holes, each below the forbidden mass range. They merged, grew, merged again, building mass through successive generations of collisions. GW 231123 represents at least a second-generation merger, possibly third. The black holes in that system aren't the direct products of stellar collapse but the accumulated remnants of multiple merger events stretching back through cosmic history. This raises profound questions about where these mergers occur. In the sparse environment of isolated space, the probability of black holes encountering each other multiple times is vanishingly small. But place them in dense stellar clusters, globular clusters containing hundreds of thousands of stars packed into volumes just tens of light-years across, and the dynamics change completely. Black holes sink to the center of these clusters through gravitational interactions. They accumulate there, a population of stellar remnants concentrated in the cluster core where encounters become frequent. A black hole merges, remains in the cluster, and can merge again when it encounters another black hole. The spin measurements from these massive mergers tell the same story. Both black holes in GW 231123 were rapidly rotating, another signature inconsistent with direct stellar collapse. When a massive star collapses, angular momentum is conserved, but the resulting black hole typically doesn't spin at extreme rates. Mergers, however, produce rapidly spinning remnants. The orbital angular momentum of the binary converts to spin in the final black hole. A second-generation black hole inherits high spin from its formation merger and carries that signature into subsequent collisions. We're uncovering a hidden population. Black holes that have grown through multiple mergers, objects that standard models didn't predict, systems that challenge our understanding of how black holes form and evolve. The detection rate suggests these events aren't rare. In dense stellar environments across the universe, black holes are colliding and merging repeatedly, building mass and spin through generation after generation of violent collisions. But the most unexpected discovery came in November 2024, and it challenged a fundamental assumption about black hole mergers. We've always understood these events as dark. Black holes emit no light. They're defined by the fact that nothing, not even electromagnetic radiation, escapes their event horizons. When two black holes merge, the collision produces gravitational waves but remains invisible to conventional telescopes. It's a purely gravitational event. On November 25, 2024, LIGO detected gravitational waves from a binary black hole merger designated S241125N. The signal indicated a collision between two black holes totaling over 100 solar masses, merging at a distance corresponding to a redshift of approximately 0.73, roughly 6.7 billion light-years away. Standard detection. Except 11 seconds after the gravitational wave signal arrived, NASA's Swift Observatory detected a short gamma-ray burst from the same region of the sky. Seconds later, China's Einstein probe satellite found an X-ray afterglow in that location. This shouldn't happen. Black hole mergers are gravitational events. They don't produce gamma-ray bursts or X-ray afterglows. Those emissions require matter, gas being heated, accelerated, compressed. But space around merging black holes in isolation is essentially empty. There's nothing there to produce electromagnetic radiation. Unless the merger didn't occur in isolation. Scientists simulated what would happen if two stellar mass black holes, the kind we've been detecting, collided inside the accretion disk of a supermassive black hole. Not in empty space, but embedded within a dense disk of gas spiraling into a galactic nucleus, a supermassive black hole millions or billions of times more massive than the Sun, actively feeding on surrounding material. The scenario is extreme but plausible. Active galactic nuclei harbor supermassive black holes surrounded by thick accretion disks. Within those disks, stellar mass black holes can orbit, embedded in dense gas. If two of them encounter each other and merge within the disk, the newly formed black hole violently disrupts the surrounding gas. Material is shocked, heated to millions of degrees, and accelerated. The interaction produces exactly what was observed, a gamma-ray burst followed by an X-ray afterglow. S241125N potentially represents the first multi-messenger detection of a black hole merger. Gravitational waves carrying information about the masses, spins, and dynamics of the collision, combined with electromagnetic observations revealing the environment where the merger occurred. It's a completely new way to study these events, linking gravitational wave astronomy with traditional observational techniques. The implications are staggering. If black hole mergers in accretion disks produce detectable electromagnetic counterparts, we can localize them far more precisely than with gravitational waves alone. LIGO can determine the source location only within large regions of the sky, sometimes hundreds of square degrees. But electromagnetic observations pinpoint sources to arcseconds or better. That precision allows follow-up studies with optical, infrared, and radio telescopes, revealing the host galaxy, the environment, the physics of the merger in unprecedented detail. It also suggests that environments like active galactic nuclei are factories for black hole mergers. Dense gas disks provide a medium where black holes can lose energy through interactions with surrounding material, causing their orbits to decay faster than gravitational wave emission alone would allow. The disks also capture black holes, concentrating them in regions where encounters and mergers become frequent. These environments could produce hierarchical mergers at rates far exceeding isolated binary evolution. But confirming S241125N as a genuine association requires careful analysis. Gamma-ray bursts occur frequently across the sky. The spatial and temporal coincidence could be chance. Statistical analysis is ongoing, examining the probability that an unrelated gamma-ray burst happened to occur in the same sky region within seconds of a gravitational wave detection. Early assessments suggest the association is real, but verification demands rigorous testing. Meanwhile, the search for supermassive black hole mergers continues through different methods. LIGO detects stellar mass black holes, objects from a few to hundreds of solar masses. But supermassive black holes, millions to billions of solar masses, produce gravitational waves with wavelengths far too long for ground-based detectors. Their mergers require space-based observatories like the planned LIGO mission, 3 spacecraft in heliocentric orbit forming a triangular detector with arm lengths of millions of kilometers. LIGO will detect supermassive black hole mergers across cosmic time, observing collisions that occurred when the universe was young. These mergers happen when galaxies collide, their central supermassive black holes spiraling together over millions of years. The process is slow but inevitable. As galaxies merge, their black holes sink toward the center of the combined system through a process called dynamical friction. Stars and gas exert gravitational drag, extracting energy from the black hole's orbit and causing them to spiral inward. Yet there's a problem. As the black holes approach each other, they eject stars through gravitational slingshot interactions. The central density drops. Eventually, so few stars remain nearby that dynamical friction becomes ineffective. The black holes stall at a separation of roughly 1 parsec, about 3 light years. Gravitational wave emission becomes efficient only at much smaller separations, around 0.01 to 0.001 parsecs. How do supermassive black holes bridge that gap? This is the final parsec problem, one of the major unsolved questions in black hole astrophysics. Various solutions have been proposed. Gas disks could provide additional drag. Interactions with a third black hole might eject one member of the binary, allowing the remaining pair to merge. Triple systems or eccentric orbits could enhance gravitational wave emission. But observational confirmation remains elusive. What we do know is that supermassive black holes have merged throughout cosmic history. Our own Milky Way's central black hole, Sagittarius A star, shows evidence of a major merger approximately 9 billion years ago. The black hole's spin axis is misaligned with the galactic plane, and it rotates at a rate inconsistent with gradual accretion alone. The most plausible explanation involves a merger with another supermassive black hole, likely from a satellite galaxy that collided with the Milky Way in the distant past. That merger reshaped the entire system. The spin vector tilted. The rotation rate increased. Evidence written in the black hole's current properties points backward to a violent collision billions of years in the past. This finding transforms how we understand supermassive black hole growth. They don't just accumulate matter gradually. They cannibalize each other through mergers, building mass through cosmic violence rather than patient accretion. LIGO will observe these events directly. Scheduled for launch in the 2030s, the mission consists of 3 spacecraft arranged in a triangle, each separated by 2.5 million kilometers. Laser beams connect the spacecraft, forming an interferometer vast enough to detect gravitational waves from supermassive black hole mergers occurring billions of light years away. The mission will observe collisions throughout cosmic history, watching supermassive black holes merge when the universe was young, when galaxies formed more frequently and collisions were common. Before LIGO launches, astronomers are finding supermassive black hole pairs using conventional telescopes. UGC 4211, a pair of merging galaxies observed with ALMA, contains 2 supermassive black holes separated by just 750 light-years. That's remarkably close on cosmic scales. The black holes orbit each other, embedded in dense gas clouds that fuel their growth while simultaneously extracting orbital energy. Over the next 100 million years, they'll spiral inward until gravitational waves dominate the energy loss. Then the merger accelerates. MCG 03-34-64 harbors an even closer pair, though confirmation across multiple wavelengths remains incomplete. Radio observations suggest 2 supermassive black holes orbiting at separations smaller than what's been clearly resolved elsewhere. If confirmed, this system represents one of the tightest known supermassive black hole binaries, offering a preview of what LIGO will routinely detect. PKS 1302-102 presents a different puzzle. Observations suggest 2 supermassive black holes in the intermediate separation range, roughly 1 parsec apart. This places them squarely within the final parsec problem zone, where conventional mechanisms struggle to explain continued orbital decay. Yet they appear to be merging anyway. Either we're witnessing a rare snapshot of a stalled binary, or some mechanism we don't fully understand is operating. Gas interactions offer one solution. Simulations show that circumbinary disks, gas rotating around both black holes, can exert torques that extract orbital energy. As gas flows inward, gravitational interactions transfer angular momentum from the binary to the disk. The black holes move closer together. This process works efficiently in gas-rich environments, potentially bridging the final parsec gap in galaxies with abundant fuel. Triple black hole systems provide another pathway. If a third supermassive black hole enters the system, free body interactions become chaotic. One black hole might be ejected entirely, carrying away orbital energy and allowing the remaining pair to merge. Alternatively, the third black hole could perturb the binary into a highly eccentric orbit. Eccentric orbits radiate gravitational waves more efficiently than circular ones, potentially shrinking the separation enough for gravitational waves to take over completely. Stellar interactions might also contribute. Although individual star scatterings become ineffective at small separations, a sufficiently dense stellar cusp could maintain high enough interaction rates. Each star passing near the binary extracts a small amount of energy. Cumulatively, enough stars might harden the binary beyond the final parsec barrier. Which mechanism dominates remains unclear. Likely, multiple processes operate simultaneously, with their relative importance depending on the specific galactic environment. Gas-rich mergers favor disk interactions. Dry mergers rely more on stellar dynamics or triple systems. Observational constraints remain limited because we can't directly observe the final parsec region with current technology. That's about to change. LISA will detect supermassive black hole mergers in progress, measuring their masses, spins, and orbital parameters with precision. By comparing observed merger rates with theoretical predictions, we'll determine which mechanisms actually operate in nature. The final parsec problem will transition from theoretical puzzle to observational question. Meanwhile, stellar mass black hole mergers continue revealing surprises. GW150914, the first detection, involved black holes of 36 and 29 solar masses. Simple numbers that revolutionized astronomy. The merger released 3 solar masses worth of energy as gravitational waves. 3 entire suns converted to pure gravitational radiation in less than a second. Understanding that energy release requires grasping the extreme physics of the final moments. As black holes spiral together, their orbital velocity approaches a significant fraction of light speed. Time dilation becomes severe. Space curves intensely. General relativity predicts that in the final milliseconds, the black holes collide at nearly half the speed of light. The impact is not a physical crash, there are no surfaces, but a violent merger of spacetime geometries. During those final 20 milliseconds, GW150914 radiated gravitational wave energy at a rate exceeding 3.6 times 10 to the 49th watts. That number is almost meaningless without context. It exceeds the combined light output of every star in the observable universe. For a brief instant, 2 colliding black holes, invisible to all electromagnetic telescopes, outshone the entire visible cosmos in gravitational waves. The energy comes from mass conversion. Einstein's equation, E equals mc squared, governs the process. 3 solar masses, approximately 6 times 10 to the 30th kilograms, multiplied by the speed of light squared. The result is 1.8 times 10 to the 47th joules. That's the energy content of 3 suns, released as gravitational radiation propagating outward at light speed. For comparison, consider supernovae. A typical Type II supernova releases about 10 to the 44th joules over several seconds. Hypernovae, the most powerful stellar explosions, reach perhaps 10 to the 46th joules. GW150914 exceeded a hypernova by more than 10 times, and it did so in a fraction of a second. Black hole mergers represent the most energetic events in the universe since the Big Bang itself. Supermassive black hole mergers dwarf even these numbers. Scale up to black holes of 100 million solar masses each. The final second of their merger radiates energy thousands of times greater than all stars in the visible universe combined over that same time frame. The gravitational wave amplitude scales with mass. Supermassive collisions produce waves so powerful they'll be detectable across the observable universe once LIGO begins operations. These aren't just impressive numbers. They're testable predictions. Each gravitational wave detection encodes information about the merging black holes. Mass determines the frequency. Spin affects the waveform shape. Distance sets the amplitude. By analyzing the signal, scientists extract physical parameters describing objects billions of light-years away. GW250114 provided the clearest signal yet detected. Signal-to-noise ratio around 77 to 80, nearly twice the previous record. The exceptional quality enabled unprecedented tests of general relativity. Scientists identified the first overtone in the ring-down phase, subtle harmonics that ring out as the newly merged black hole settles into equilibrium. These overtones carry independent information about the final black hole's properties. The ring-down itself validates general relativity under extreme conditions. When two black holes merge, the resulting object is initially distorted, pulsating with excess energy. It quickly settles down by radiating gravitational waves in a characteristic pattern determined entirely by its mass and spin. This pattern matches predictions from the Kerr solution, the mathematical description of rotating black holes in general relativity. Measuring the ring-down frequencies tests the no-hair theorem, which states that black holes are completely characterized by just three properties: mass, spin, and electric charge. No other features matter. No internal structure, no memory of how the black hole formed. Everything collapses to those three numbers. GW250114's ring-down confirms this prediction with remarkable precision. The detection also verified Hawking's area theorem. Proposed in 1971, the theorem states that the total surface area of black holes can never decrease. When two black holes merge, the final area must equal or exceed the sum of the initial areas, even though energy escapes as gravitational waves. GW250114 provided the clearest empirical confirmation of this prediction, measuring the areas before and after merger with sufficient precision to rule out violations. These tests occur under conditions impossible to replicate on Earth. The black holes in GW250114 were dozens of solar masses, rotating at significant fractions of the maximum possible spin, colliding at relativistic velocities in regions where spacetime curvature reaches extreme values. No laboratory can approach these conditions. Gravitational wave detectors transform distant cosmic collisions into precision physics experiments. Each new detection adds to our understanding. GW231123, detected in November 2023, involved the most massive black holes ever observed through gravitational waves. The final object weighed approximately 225 solar masses, formed from progenitors of roughly 100 and 140 solar masses. Those masses fall within the Perrin stability gap, a range where standard stellar evolution forbids black hole formation. Perrin stability supernovae should completely destroy stars in this mass range. When oxygen burning begins in the core of a sufficiently massive star, the energy release creates electron-positron pairs. These pairs reduce pressure support. The core contracts. Temperature rises. Runaway thermonuclear burning detonates the entire star. Nothing remains. No neutron star, no black hole, just scattered debris. Yet GW231123's progenitors existed in the forbidden zone. How did they form? Hierarchical mergers provide one explanation. If smaller black holes merged previously, the products could reach masses in the Perrin stability gap without ever being stars. This transforms black hole populations, suggesting multiple generations of mergers build up mass progressively. GW241011 and GW241110 support this picture. Both events involved black holes with extreme spins and mass ratios suggesting hierarchical formation. The October 2024 detection showed a 20 solar mass black hole spinning at 69 to 87% of maximum, far faster than stellar collapse typically produces. The November detection revealed an anti-aligned spin, rotating opposite to the orbital direction. Both configurations point toward formation through previous mergers in dense stellar environments. These environments matter. Star clusters with high densities and massive binaries produce different merger signatures than isolated binary evolution. Black holes colliding with stars changes everything. In dense stellar clusters where black holes concentrate, interactions become common. A passing star feels gravitational forces that can accelerate it to extreme velocities. Sometimes the star escapes. Sometimes it doesn't. When a black hole captures a star gravitationally, tidal forces stretch the star along the direction toward the black hole while compressing it perpendicular to that axis. This process, called spaghettification, tears the star apart before it crosses the event horizon. Half the stellar material falls inward. The other half escapes at high velocity. The infalling gas forms an accretion disk around the black hole, heating to millions of degrees and radiating across the electromagnetic spectrum. For black holes and star clusters, stellar collisions provide something else entirely. They add spin. When a black hole consumes part of a star, it gains angular momentum from the encounter. The direction and magnitude depend on the star's trajectory relative to the black hole's existing rotation axis. Multiple collisions over millions of years build up spin progressively. This matters because spin directly affects merger signatures. Black holes born from stellar collapse typically rotate slowly, with spins around 10 to 20% of maximum. But black holes that have consumed stars or merged previously can spin much faster, approaching 70, 80, even 90% of the theoretical limit. That's exactly what recent detections reveal. For stellar clusters with high-density cores and more massive star binaries, black holes collide with high-mass stars more frequently, increasing the rate at which spinning black holes form. Studies show that for merging black hole binaries in star clusters, especially those with high metallicity, over 50% had at least one black hole that had spun up after a previous collision with a star. This creates a population of black holes fundamentally different from those formed in isolation. Their spins encode their history. Every interaction leaves a mark. The November 2025 detection pushed this further. LIGO captured an unusual gravitational wave signal designated S251112cm. The collision involved two objects far lighter than typical stellar black holes or neutron stars. Standard astrophysical processes can't explain it. The most plausible interpretation points toward primordial black holes, objects formed in the earliest moments after the Big Bang rather than from stellar collapse. If confirmed, this detection would revolutionize cosmology. Primordial black holes could account for a significant portion of dark matter, solving one of physics' deepest mysteries through gravitational wave astronomy. Primordial black holes form from density fluctuations in the early universe. Regions slightly denser than average can collapse directly into black holes without requiring stars or supernovae. These objects could have any mass, from far less than Earth to thousands of solar masses, depending on when and how they formed. Unlike stellar black holes, primordial black holes carry no chemical signatures, no spin preferences, no connection to stellar evolution. They're fossils from the universe's first fraction of a second, preserved unchanged for over 13 billion years. S251112cm's unusual mass suggests exactly this origin. The objects were too light for stellar collapse but too heavy for neutron stars. They fall into a gap where conventional formation mechanisms fail. Primordial black holes fill that gap naturally. If the detection holds up under scrutiny, it opens an entirely new window into the early universe. Gravitational waves become archaeological tools, probing conditions mere moments after the Big Bang. But detecting primordial black holes requires distinguishing them from other possibilities. Neutron-star mergers produce similar mass ranges. Exotic stellar remnants might exist in unexplored parameter space. The key lies in population statistics. If LIGO detects multiple events with similar characteristics, the primordial interpretation strengthens. A single detection remains intriguing but inconclusive. The next few years will determine whether S251112 represents a cosmic revolution or an unusual outlier. Meanwhile, the detection rate keeps accelerating. As of February 2026, LIGO has completed 4 observing runs with 391 total gravitational wave detections. The 4th run alone, spanning 23 months, produced 200 candidate events. Compare that to the first 3 runs, which detected 90 events over the same duration. Sensitivity improvements explain part of this increase. Better instruments detect fainter signals from greater distances. But merger rates also appear higher than early estimates suggested. The universe contains more colliding black holes than models predicted. This abundance transforms gravitational wave astronomy from novelty to routine. Early detections were celebrated individually. Each event warranted detailed analysis and publication. Now detections arrive faster than researchers can fully characterize them. The field shifts toward statistical studies, analyzing populations rather than individual systems. What fractions show hierarchical formation signatures? How do merger rates vary with redshift? Do environmental factors influence black hole spin systematically? The Global Detector Network enables this statistical approach. LIGO operates 2 detectors in the United States, one in Hanford, Washington, and another in Livingston, Louisiana. Virgo operates in Italy. CAGRA operates in Japan. Together, they form the LVK collaboration. Multiple detectors provide crucial advantages. When only 2 instruments observe a signal, localization remains poor, covering hundreds or thousands of square degrees on the sky. Adding a 3rd detector shrinks the uncertainty region by more than a factor of 20. For GW170814, detected by all 3 instruments, the localization covered just 60 square degrees, 10 times smaller than 2 detector networks alone. Better localization matters for multi-messenger astronomy. Gravitational waves provide precise timing and directional information. Electromagnetic telescopes can then search the indicated sky region for counterparts. This approach works best for neutron-star mergers, which produce optical and gamma-ray emission. Black hole mergers typically remain dark to conventional telescopes. The November 2024 detection S241125N changed that assumption. S241125N involved 2 black holes totaling over 100 solar masses merging at a distance corresponding to redshift approximately 0.73. Standard black hole mergers emit only gravitational waves. S241125N did something different. About 11 seconds after the gravitational wave signal, NASA's Swift Observatory detected a short gamma-ray burst from the same sky region. China's Einstein probe satellite found an X-ray afterglow shortly thereafter. This unprecedented combination suggests black hole mergers in dense environments can produce electromagnetic counterparts under specific conditions. The proposed explanation involves accretion disks. Supermassive black holes at galactic centers often have disks of gas and dust orbiting around them. Stellar mass black holes occasionally inhabit these disks, orbiting within the gas like planets in a protoplanetary disk. When two such black holes merge inside the disk, the newly formed remnant plows through surrounding material. Gas heats from the interaction, producing X-rays and gamma rays. The emission lasts only seconds to minutes, requiring rapid follow-up observations to catch. Simulations support this scenario. Researchers modeled stellar mass black holes merging inside active galactic nucleus disks. The results match S241125N's observations remarkably well. The gamma-ray burst timing, energy, and duration all align with predictions. If correct, this opens a new channel for studying black hole environments. Most mergers occur in isolation, revealing nothing about their surroundings. Mergers with electromagnetic counterparts provide environmental context, showing where and how black holes form. But S241125N remains controversial. The association between gravitational waves and electromagnetic emission could be coincidental. Gamma-ray bursts occur frequently across the sky. One happening near a gravitational wave detection by chance isn't impossible. Statistical analysis will clarify this over time. If future detections show similar patterns, the connection strengthens. If S241125N remains unique, coincidence becomes more likely. Supermassive black hole mergers present different challenges entirely. When galaxies collide, their central black holes eventually spiral together. These objects weigh millions to billions of solar masses, far exceeding stellar mass black holes. Their mergers release correspondingly more energy. Repeating the math with a pair of black holes that are 100 million solar masses each shows the energy they emit in the final second exceeds the combined energy emitted by all stars in the visible universe over that same duration by thousands of times. Yet we've never observed supermassive black hole mergers directly. LIGO can't detect them. The gravitational waves have wavelengths far too long for ground-based detectors. Earth's seismic noise and gravitational fluctuations from atmospheric density changes overwhelm signals at those frequencies. Detecting supermassive black hole mergers requires space-based instruments operating at millihertz frequencies rather than LIGO's kilohertz range. The Laser Interferometer Space Antenna, LISA, will fill this gap. Planned for launch in the mid-2030s, LISA consists of 3 spacecraft flying in triangular formation, separated by 2.5 million kilometers. Laser beams traveling between spacecraft detect gravitational wave-induced distance changes. Space provides the stable, noise-free environment necessary for millihertz observations. LISA will observe supermassive black hole mergers throughout cosmic history, from the present day back to redshifts exceeding 10, corresponding to when the universe was less than 500 million years old. Combined observations will reveal merger dynamics completely. LISA detects the inspiral phase, lasting months to years as black holes spiral closer. Ground-based detectors like LIGO observe the final moments, the last seconds before merger when orbital velocities approach light speed. Together they map the entire process, from gentle orbital decay through violent collision to final ring-down. No single detector can capture this full range. Multiband gravitational wave astronomy provides the complete picture. The closest supermassive black hole pairs identified so far remain years to millions of years from merging. Scientists using ALMA discovered 2 black holes in galaxy UGC 4211 separated by just 750 light-years, among the closest ever observed. These black holes orbit each other but haven't entered the rapid inspiral phase. Gravitational wave emission remains too weak for current detection. They'll merge eventually, in perhaps 100 million years, producing gravitational waves LIGO could detect if it were operating. Human timescales make direct observation impossible. Shift_occurs_ here. That's where our own galaxy's history becomes relevant. Evidence suggests Sagittarius A star, the supermassive black hole at the Milky Way's center, formed through a merger roughly 9 billion years ago. Researchers at UNLV analyzed its unusual properties, particularly its misaligned high-spin axis. Most supermassive black holes spin along axes roughly aligned with their host galaxy's rotation. Sagittarius A star doesn't follow this pattern. Its spin axis tilts dramatically relative to the galactic plane, suggesting violent disruption in its past. The most plausible explanation involves a collision with another supermassive black hole, likely from a satellite galaxy that merged with the Milky Way billions of years ago. The Gaia-Enceladus galaxy collided with the Milky Way approximately that long ago. When galaxies merge, their central black holes don't immediately combine. They orbit each other for millions or billions of years, gradually spiraling closer as gravitational wave emission saps orbital energy. Eventually they merge violently, producing a final black hole with properties determined by the masses, spins, and orbital configuration of the originals. If Sagittarius A star formed this way, we're living in a galaxy shaped by one of the universe's most violent events. The merger would have dramatically altered its spin magnitude and orientation. Material surrounding the black hole during that era experienced extreme gravitational forces, potentially triggering bursts of star formation or expelling gas from the galactic center. The evidence remains circumstantial but compelling. Sagittarius A star's properties make sense only if its history includes major disruption. This raises a broader question about hierarchical growth. Black holes don't form at their current masses. They grow over cosmic time through two primary mechanisms. Accretion involves pulling in surrounding gas and stars, gradually adding mass. Mergers combine two black holes instantly, creating a more massive remnant. For supermassive black holes weighing millions or billions of solar masses, mergers play crucial roles in their evolution. Observations increasingly suggest many supermassive black holes experienced multiple mergers throughout their histories. Stellar mass black holes show similar patterns. Recent detections reveal hierarchical mergers where black holes formed from earlier collisions merge again. GW241011, detected in October 2024, involved black holes of 20 and 6 solar masses. The larger black hole spun at 69 to 87% of the maximum possible rate. Black holes born from stellar collapse typically spin far slower. Such extreme rotation indicates formation through merger rather than stellar death. 1 month later, GW241110 showed similar signatures. The system involved black holes of 17 and 8 solar masses. The larger black hole spun rapidly but with its axis anti-aligned relative to the orbital plane. Conventional stellar evolution can't explain this configuration. If both black holes formed from the same stellar system, their spins should align with the orbital axis. Anti-alignment suggests chaotic formation in dense environments where black holes encounter each other randomly. These observations point toward dense stellar clusters as hierarchical merger factories. Globular clusters and nuclear star clusters pack thousands to millions of stars into compact volumes. Black holes sink toward cluster centers through dynamical friction. Once concentrated, they encounter each other frequently. Some encounters produce bound binaries that eventually merge. Others involve direct collisions between black holes already in binaries, creating second or third generation black holes. Why does spin matter so much? A black hole's spin encodes its formation history. Stellar collapse produces black holes with relatively low spins, typically below 30% of maximum. Mergers add angular momentum from orbital motion, spinning up the remnant. Repeated mergers build spin progressively. Measuring spin therefore reveals whether a black hole formed directly from a star or through one or more mergers. The spin measurements themselves represent remarkable achievements. Gravitational wave signals contain information about both masses and spins. During in-spiral, spin affects orbital dynamics through spin-orbit coupling and spin-spin interactions. Different spin configurations produce subtly different waveforms. Extracting these differences requires extremely clean signals. GW241011 and GW241110 provided sufficient signal quality for precise spin measurements. But hierarchical mergers create theoretical puzzles. Black holes lose energy through gravitational wave emission, causing orbits to decay. In isolation, this process works efficiently. In dense clusters, other stars and black holes gravitationally perturb the binary, potentially ejecting it from the cluster before merger. The fact that we observe hierarchical mergers means clusters must retain some black hole binaries long enough for them to merge, then retain the remnant long enough for it to merge again. Computer simulations help resolve this. Models of dense clusters show that while many black hole binaries get ejected, some remain bound to the cluster. These survivors eventually merge within the cluster. The remnant black hole, now more massive than average, sinks back toward the cluster center where it may capture another black hole and merge again. This process can repeat multiple times in the densest clusters. The GW231123 event from November 2023 pushes this scenario further. That merger produced a final black hole of 225 solar masses, formed from black holes of approximately 100 and 140 solar masses. These masses fall within a theoretically forbidden range called the parainstability gap. Stars massive enough to produce black holes in this range should instead explode completely in parainstability supernovae, leaving no remnant. How do we observe black holes that shouldn't exist? Hierarchical mergers provide the answer. If two smaller black holes, each below the gap, merge, their remnant can land within the forbidden mass range. GW231123 likely represents exactly this scenario, a second or third generation black hole formed through multiple mergers. The rapidly spinning components support this interpretation. These discoveries fundamentally change our understanding of black hole populations. Before gravitational wave astronomy, we knew about two black hole populations. Stellar mass black holes weighing a few to perhaps 20 solar masses formed from stellar collapse. Supermassive black holes weighing millions to billions of solar masses occupied galactic centers. A gap existed between these populations. Gravitational wave detections fill that gap. We now observe black holes of all masses from a few solar masses up to hundreds of solar masses. Many fall in ranges difficult to explain through stellar evolution alone. Hierarchical mergers provide the missing formation mechanism, creating black holes across the entire mass spectrum through successive collisions. This process may explain how supermassive black holes formed in the early universe. Observations reveal supermassive black holes weighing billions of solar masses when the universe was less than 1 billion years old. Growing black holes this massive through accretion alone requires unrealistically high accretion rates sustained over hundreds of millions of years. Hierarchical mergers offer an alternative pathway, building massive black holes quickly through repeated collisions in dense environments. The detection rate itself reveals unexpected information. LIGO's fourth observing run alone detected approximately 200 gravitational wave candidates. Previous runs spanning similar durations detected 90 events combined. Sensitivity improvements explain part of this increase. Better detectors see farther into space, accessing larger volumes and more potential sources. But the sheer number of detections suggests black hole mergers occur more frequently than early predictions indicated. Statistical analysis of the detected population provides insights into formation channels. Mergers from isolated binary evolution produce different distributions of masses, spins, and other properties compared to dynamical formation in clusters. By analyzing hundreds of events, researchers identify which formation channels dominate at different masses. Current data suggests both channels contribute significantly, with dynamical formation becoming increasingly important at higher masses. Each detection also tests general relativity under extreme conditions. Black hole mergers produce the strongest gravitational fields we can observe. Spacetime curvature near merging black holes reaches values impossible to recreate in laboratories. The signals themselves encode information about how gravity behaves in these regimes. So far, every observation matches general relativity's predictions with remarkable precision. GW250114, detected in January 2025, provided the clearest test yet. With a signal-to-noise ratio near 80, far exceeding previous detections, the data quality allowed measurements impossible with noisier signals. Researchers identified multiple harmonics in the ring-down phase, the reverberations as the merged black hole settled into its final state. These harmonics precisely matched predictions from general relativity for a rotating black hole. This observation confirmed Hawking's area theorem with unprecedented precision. The theorem states that the total surface area of black hole event horizons never decreases. When two black holes merge, the final black hole's area must equal or exceed the sum of the original areas. GW250114's exceptional data quality allowed direct verification. The measured areas before and after merger aligned perfectly with the theorem's predictions. But perhaps the most intriguing recent development involves primordial black holes. In November 2025, LIGO detected signal S251112 involving objects far lighter than typical stellar black holes. The masses fell below theoretical limits for stellar collapse. One possibility remains highly speculative but fascinating. These could be primordial black holes, formed in the universe's first moments rather than from stellar death. If primordial black holes exist, they could explain dark matter, the invisible substance comprising 85% of the universe's matter. Current dark matter candidates include exotic particles never directly detected despite decades of searching. Primordial black holes offer an alternative, dark matter made of normal matter compressed into black holes during the Big Bang. Detecting primordial black hole mergers would revolutionize cosmology and particle physics simultaneously. The evidence remains preliminary. S251112 could represent unusual stellar mass black holes rather than primordial objects. Distinguishing between these scenarios requires more detections with similar properties. If LIGO observes multiple low-mass mergers that can't be explained through stellar evolution, the primordial hypothesis strengthens. Statistical analysis over coming years will clarify whether we've detected the first primordial black holes or simply the low-mass tail of the stellar population. Beyond stellar mass black holes lies an entirely different scale of cosmic collision. Supermassive black holes, millions to billions of times the mass of our Sun, sit at the centers of most galaxies. When galaxies merge, their central black holes eventually spiral together. These mergers dwarf anything LIGO has detected. The energy released exceeds stellar mass collisions by factors of thousands or millions. Consider two supermassive black holes, each 100 million solar masses. During their final second of spiraling together, they emit more energy than every star in the observable universe combined over that same time frame. not just more than our galaxy. Every galaxy we can see, billions of them, all their stars added together. The supermassive merger still wins. But detecting these events presents enormous challenges. LIGO's sensitivity range works perfectly for stellar mass black holes. Their mergers produce gravitational waves with frequencies LIGO's kilometer-scale arms can measure. Supermassive mergers generate much longer wavelengths. These low-frequency waves pass right through ground-based detectors without registering. Earth's seismic noise alone would drown them out. Observing supermassive mergers requires detectors in space. LISA, the Laser Interferometer Space Antenna, represents the next frontier. Free spacecraft flying in triangular formation, separated by millions of kilometers. No ground vibrations. No atmospheric disturbances. Just pure signal from the universe's largest collisions. LISA won't launch until the 2030s. Meanwhile, astronomers search for supermassive pairs approaching merger. The galaxy UGC 4211 contains two supermassive black holes just 750 light-years apart. Both actively feeding, both growing. Eventually they'll spiral together. But eventually means millions of years. The final stages occur far too slowly for human observation. Theoretical models predict how these mergers unfold. Two galaxies collide. Their supermassive black holes begin orbiting each other at vast distances. Stars and gas between them gradually extract orbital energy, causing the black holes to sink toward the galactic center. This process takes hundreds of millions of years. Once separated by just a few parsecs, gravitational wave emission begins dominating the energy loss. The orbit shrinks faster. Years become decades, decades become minutes, minutes become fractions of seconds. Then comes the final parsec problem. As orbital separation drops below 1 parsec, the volume of space the black holes sweep through contains very little matter. Stars and gas that could extract energy become scarce. Gravitational waves alone can't shrink the orbit efficiently until separation reaches much smaller values, around 1/100th of a parsec. Theory suggests these systems should stall, never quite merging within the universe's age. Yet merged supermassive black holes clearly exist. Our own Milky Way's central black hole, Sagittarius A*, shows unusual characteristics. Its spin axis points in an unexpected direction. Its rotation rate seems too high for simple formation scenarios. One explanation fits the observations remarkably well. Sagittarius A* formed through merger, likely around 9 billion years ago when the Milky Way absorbed another galaxy called Gaia Enceladus. Something overcomes the final parsec problem. Proposed solutions involve additional matter, perhaps through gas inflows or star clusters, providing the necessary energy extraction. Understanding this mechanism matters for predicting merger rates and gravitational wave signals LISA will detect. November 2024 brought an unexpected breakthrough in black hole merger observations. LIGO detected gravitational waves from event S241125N, a merger of two black holes totaling over 100 solar masses. Typical detection. Except 11 seconds later, NASA's Swift satellite observed a gamma-ray burst from the same sky region. China's Einstein probe satellite confirmed an X-ray afterglow. Black hole mergers shouldn't produce light. They're dark by definition, emitting no electromagnetic radiation. Yet here was a clear correlation. Gravitational waves followed by gamma rays and X-rays from the same source. The explanation involves environment. Most black hole mergers occur in empty space, far from any matter. S241125N likely happened somewhere very different. The accretion disk surrounding a supermassive black hole. Imagine two stellar mass black holes spiraling together inside the swirling gas feeding a galactic center. The merger creates a new, larger black hole moving through dense material. Interactions with surrounding gas generate shocks, heating, particle acceleration. Result: gamma rays and X-rays detectable across billions of light-years. This opens multi-messenger astronomy for black hole mergers. Gravitational waves tell us about the collision itself. Electromagnetic observations reveal the environment, the context where the merger occurred. Combined, they provide far more information than either signal alone. Future detectors will transform our observational capabilities. LISA launching in the 2030s will detect supermassive mergers years before they occur. The gravitational wave signal grows steadily louder as black holes spiral closer. LISA will track this progression, predicting the final merger days or weeks in advance. Electromagnetic telescopes can then prepare, watching the exact sky location at the precise moment. The European Space Agency plans another mission, Athena, an X-ray telescope with unprecedented sensitivity. LISA detects the gravitational waves, pinpointing the merger location. Athena observes the X-ray emission from gas surrounding the black holes. Together they'll reveal how supermassive mergers affect their host galaxies, how material funnels into the merged black hole, how energy released influences star formation across vast regions. Ground-based detectors continue improving. LIGO's fifth observing run, scheduled for the late 2020s, will feature enhanced sensitivity. Squeezed light technologies reduce quantum noise. Better seismic isolation minimizes vibrations. Advanced data analysis extracts signals from increasingly noisy backgrounds. Detection rates will climb further, potentially reaching thousands of events per year. Japan's Kagra detector recently joined full operation. Despite challenges with seismic noise in Japan, Kagra's underground location and cryogenic mirrors offer unique advantages. India plans constructing LIGO India, adding another detector to the global network. More detectors mean better sky localization, faster source identification, improved parameter estimation. Each technological advance reveals new populations. Early LIGO runs detected only the loudest, nearest mergers. Improved sensitivity reaches fainter, more distant sources. Statistical analysis of these populations tests formation theories, constrains merger rates across cosmic history, maps how black hole demographics evolved over billions of years. Theoretical work complements observations. Numerical relativity simulations model mergers with increasing accuracy. These simulations predict gravitational waveforms for specific scenarios, eccentric orbits, extreme mass ratios, unusual spin configurations. Comparing predictions with observations determines which formation channels dominate. Recent simulations focused on head-on collisions, black holes approaching along nearly radial trajectories rather than circular orbits. These produce distinctive waveforms with strong late-time tails, slowly decaying signals carrying information about spacetime structure far from the black holes. Detecting these tails requires exceptional data quality, but they offer unique tests of general relativity. The ring-down phase provides another testing ground. After merger, the final black hole vibrates like a struck bell, emitting gravitational waves at specific frequencies determined entirely by mass and spin. General relativity predicts these frequencies with extraordinary precision. Observations matching predictions validate the theory. Deviations would hint at new physics. GW250114's exceptional signal quality allowed measuring multiple ring-down harmonics. Like musical overtones, these harmonics form a precise pattern. The detected pattern matched general relativity's predictions perfectly. Any alternative gravity theory must reproduce this match while remaining consistent with other observations. Black hole physics connects to fundamental questions beyond astrophysics. Do primordial black holes exist? If S251112 cm and similar detections represent primordial objects, they solve the dark matter mystery. 85% of the universe's matter, explained not through exotic particles but through black holes formed in the Big Bang's first moments. Testing this hypothesis requires more data. One detection proves nothing. 10 detections with similar properties suggest a real population. 100 detections allows statistical analysis, determining whether observed masses and rates match primordial predictions or indicate unusual stellar mass black holes. The coming decade promises answers. Detector sensitivity improvements, longer observing runs, advanced analysis techniques. By 2035, gravitational wave astronomy will have cataloged thousands of mergers, mapped black hole populations across cosmic time, tested general relativity under conditions impossible to replicate anywhere else. LIGO will observe supermassive mergers directly, watching the final years of billion solar mass collisions. Multi-messenger observations will reveal how mergers shape galaxies, trigger star formation, influence cosmic evolution. The electromagnetic counterparts to black hole mergers may become routine, offering insights into environments where these catastrophic events occur. Each detection answers old questions while raising new ones. Why do some black holes spin rapidly while others barely rotate? How common are hierarchical mergers? What fraction of supermassive black holes formed through collisions versus continuous accretion? Does the final parsec problem have a universal solution or multiple pathways depending on environment? Black hole collisions represent nature's most violent events. Spacetime itself warps beyond recognition. Energy output exceeds the combined light of billions of galaxies. Matter compressed to infinite density. Physics tested at absolute extremes. We've barely begun exploring this realm. 10 years ago, gravitational waves remained theoretical predictions. Today, we detect hundreds of mergers, measure their properties, test fundamental theories. Tomorrow, we'll observe the universe's largest collisions, watch supermassive black holes spiral together, potentially detect the primordial black holes that may constitute dark matter itself. The cosmos speaks through gravitational waves. We've learned to listen. What we're hearing transforms our understanding of reality. The technology detecting these signals represents humanity's most precise measurement ever achieved. LIGO measures distance changes 1/10,000th the diameter of a proton across 4 kilometers. Proportionally, that's like measuring the distance to the nearest star and accounting for variations smaller than a human hair's width. Every passing truck, every distant earthquake, every thermal fluctuation in the mirrors creates noise dwarfing the signal. Yet we filter through this chaos, extracting gravitational waves from black hole collisions billions of light years away. Free detector networks now operate globally. LIGO's twin facilities in the United States, Virgo in Italy, Kagra in Japan. When only 2 instruments observe a signal, the source location covers hundreds of square degrees on the sky. Adding a third detector shrinks uncertainty by more than 20 times. GW170814, detected by all 3, localized to just 60 square degrees. That precision enables electromagnetic follow-up, searching for counterparts to gravitational wave events. The global network continues expanding. India plans constructing LIGO India, adding another detector. Each addition improves localization, increases detection confidence, enables new science. By the early 2030s, 4 or 5 detectors may operate simultaneously, pinpointing sources to arc minutes rather than degrees. But ground-based detectors have fundamental limits. They detect stellar mass black holes perfectly. Supermassive mergers remain beyond reach. Those gravitational waves have wavelengths too long, frequencies too low. Earth's seismic noise drowns them completely. Observing the universe's largest collisions requires leaving Earth entirely. LIGO changes that calculation. Free spacecraft in solar orbit, separated by millions of kilometers. No ground vibrations. No atmospheric disturbances. Pure gravitational wave signals from supermassive black hole mergers across cosmic history. LIGO will detect these events years before they occur, watching signals grow steadily louder as black holes spiral closer. Electromagnetic observatories can prepare, watching the exact location at the predicted moment. Combined observations reveal merger environments completely. Gravitational waves describe the collision itself, masses, spins, orbital dynamics. Electromagnetic signals show surrounding gas, how the merger affects star formation, how energy propagates through the host galaxy. Multi-messenger astronomy transforms black hole mergers from invisible events into complete physical laboratories. The implications extend beyond astrophysics. Every detection tests general relativity where gravity reaches maximum strength. Space-time curvature near merging black holes exceeds anything achievable in laboratories. The signals encode how gravity behaves under these conditions. So far, perfect agreement with Einstein's predictions. But each new detection probes unexplored parameter space, searching for deviations that might reveal new physics. Black hole mergers also connect to cosmology. If primordial black holes exist, they solve the dark matter mystery. 85% of the universe's matter, explained through objects formed in the Big Bang's first fraction of a second. S251112 cm hints at this possibility. The masses fell below stellar collapse limits. Multiple similar detections would confirm a primordial population, revolutionizing our understanding of both dark matter and the early universe. Formation channels remain partially mysterious. Isolated binary evolution produces some mergers. Dynamical encounters in dense clusters produce others. Hierarchical mergers, black holes formed from earlier collisions, create a third channel. Current data suggests all three operate simultaneously, with their relative importance varying by mass and environment. Future observations will quantify these channels precisely. The detection rate itself exceeded predictions. Early estimates suggested LIGO might observe a few mergers per year. Reality delivered hundreds annually. Either black hole mergers occur more frequently than expected, or formation channels we didn't anticipate dominate the population. Probably both. The universe contains more colliding black holes than models suggested, and they form through more pathways than we imagined. Each merger represents a cosmic endpoint. Two massive stars formed billions of years ago. They evolved, exploded, left behind black holes. Those black holes orbited for eons, gradually spiraling closer. Finally, in a fraction of a second, they collided, releasing more energy than all the stars in the observable universe combined. The gravitational waves from that collision traveled through expanding space for billions of years, eventually reaching Earth where detectors measured their passage. We're witnessing events from the universe's deep past. GW150914 occurred 1.3 billion years ago, when Earth was dominated by simple multicellular organisms. GW231123 happened over 5 billion years ago, before our solar system existed. These signals carry information across cosmic time, revealing how black holes behaved when the universe was fundamentally different. The coming decade promises exponential growth in discoveries. Detector sensitivity improves continuously. Observing runs lengthen. Analysis techniques advance. By 2035, we'll have cataloged thousands of mergers, mapped black hole demographics across cosmic history, tested general relativity under every accessible condition. LIGO's launch will open supermassive merger observations, revealing how billion solar-mass black holes collide and reshape galaxies. Multi-messenger astronomy may become routine as more mergers show electromagnetic counterparts. Primordial black hole searches will either confirm their existence or rule them out definitively. Black hole collisions represent physics at absolute extremes. Infinite density. Warped spacetime. Energy release beyond comprehension. These events occurred in darkness and silence, invisible to conventional telescopes, detectable only through the gravitational waves they generated. We've learned to observe the unobservable, measuring ripples in spacetime itself from collisions that outshine the entire universe. The universe speaks through gravitational waves. After a century of theoretical predictions and technological development, we've finally learned to listen. And what we're hearing rewrites fundamental physics, one violent collision at a time.